So I have trained my model and you can see it took me around 1400 seconds. So that is around 20 minutes. And you can see I've achieved an accuracy of 90%. That is completely fine considering that it is our custom neural network that you have designed. And uh, before that, I just also, should mention here that there was some typo. It should be underscore here that was, missing in the previous video where I used that dash. And then here in start time, I added a parenthesis as well that will have to remove. Anyhow, once you do that, you should be able to run this without any error. And the first thing that you should do after you have trained your model is right away to save the model, save the trained model, because you cannot be spending this much amount of time again and again. So for that you'll say torch.save and you'll say CNN model, the name of the model, dot state underscore dictionary, comma, whatever the name that you want to say. I'll say custom model or custom CNN model, whatever, dot pt. That's the format, and you run that. There you go. So if you check this, you can see I have stored this model over here, right? Wherever you are running your notebook, it should be in the same folder. One more thing is I just mentioned that, we have gotten the accuracy. So let us, try to plot this out. I'll say plt.plot, and that is inside this will have a list comprehension that is t by 80 for every t in this train correct. All right, and the label would be the training accuracy. And if I just plot this out very quickly, there you go, very good. But I'll just make some changes here. For the starters, I'll say this is t by 30 and this is for test correct, and this is validation accuracy. And then I'll say plt.title, pass in the accuracy at the end of each epoch. I'll say plt.legend. I'll say plt.show over here. So you can see here, there's the training accuracy, there's the validation accuracy. Well, this was our custom model that we have designed. The architecture is something that we have designed and we have trained it. Now, what you can also do is use a number of pre-trained model as well. So Torch Vision actually provides a number of proven models that is available in Torch Vision pre-trained model provided by Torch Vision. Okay. So now there are a bunch of models which are trained on ImageNet dataset. Maybe I'll take, I'll take one of the, I'll make a video on those in the future. But for now, I'll use AlexNet as one of our model, right? So I'll say models dot, and again, models is the module that we have imported previously in our library. You can see Torch Vision. From Torch Vision, we have imported the models. I'll say models dot AlexNet. AlexNet. Again, this is just one of the model. There are several other models like, VGG, ResNet, SqueezeNet, DenseNet, Inception, ShuffleNet, MobileNet, and so many more. But here I'm just using this very, AlexNet because it is, I think, very simple and very effective. So I'll say pre-trained equal to true. And again, this is a pre-trained model, right? So if I just assign this to AlexNet here as the variable. And here I'll say AlexNet again. Here and that. There we go. So this is the model. Again, I have not designed it. This is the model that is being provided by, Torch Vision itself. All right. Now, what I want to do here, I want to first of all freeze the pre-trained weights and biases. Why? Because I'll be making some changes to this model. So I'll say that um, freezing feature parameter. So whatever the changes that I make in the model, it's not going to affect the parameter itself, right? Why we are doing that, I'll show you shortly. I'll say for parameter in AlexNet model, AlexNet dot parameters here, and then I'll say parameters dot requires grad equal to true. All right. Now, next we need to modify the fully connected layer to produce a binary output because that is what is desired. In our case, since it's a cat versus dog, so it can be either cat or dog. Basically, we have to make some changes to this. And for that, what we'll do first of all is I'll say set a manual seed so that I can get the same result, and again we can reproduce the result. You can set any other seed, 50, 40, whatever. So I'll say this, and then I'll say model AlexNet dot classifier is something that I'm going to change. That is, I'll say nn dot sequential, nn dot linear is the first thing is 9216, that is the input as it is, and then I'll make the changes. I'll not go to 4096, I'll go to 1024. All right, and then I'll say nn dot relu, there you go. Then nn dot dropout, pass in 0.4. So I'll basically dropping out any 40% of the neuron. Again, very optional and very empirical as well. You can always play around with this number. And then dot linear, I'm just straight away going from 1024 to 2. Again, design the network as per your requirement. We have already seen that how to design the network. Then I'll say nn dot log softmax. So I'm taking very simple model here, 9216. That is the first layer, input layer, then the one hidden layer 1024, and the output layer 2. That's it. And then I'll say dimension equal to 1. Remember, my model is already trained. Okay, I'm not changing that thing. I have to add one more parenthesis. And then if I just check this AlexNet model, you can see that this is now the model that we have vis-a-vis the previous one. So it had this much more this many hidden layers and all that. You can say output feature is still 1000. Again, if you want, you can add one more layer, just like how you have here that 4096. So maybe instead of 1024 you'll put 4096, then from 4096 you can go to 1000. So it will be just like how it is over here. And dropout is 0.5. You can set it that as well. Again, it is on it is as per you here. But I'm going from 9216 to 1024 and straight away to the binary classification, that is 2. Okay, now why it is needed? Because again, in output layer we have 1000 outputs. That is not the case. That is not going to work in our case because we have just two in outputs here, binary output, cat or dog, and that is why the output layer has to have two. Any other thing, the binary, sorry, the hidden layers and the dropouts and something like that, you can always go ahead and change by yourself, right? Now what I'm going to do is I'm going to say count parameters. Is this the name, I think, of the function? Oh, we have not created a function here. That's not a good news actually. So in that case, what I'll do is I'll just copy this as it is, come back, and I'll, instead of CNN model, I'll just pass in the AlexNet dot parameter. Right now, if you run that, there you go. So these are the number of parameters that you have. A huge number here. I don't know what is the exact number, but you can take out your calculator. You can just do a copy paste. But it is fairly large number. That is the point. Okay, great. So these are the trainable parameter that we have. I'll just put a note here. Do you understand what is the thing? So these are the trainable parameters. Now I have to train this on my on my image here as well. So for that, first of all, the everything is going to remain the same. I'll copy this. Okay, come back, right? Remove CNN model because that is not what I want. Remove this as well. Criterion will remain the same. Manual seed. Okay, we can put a manual seed here as well. And here I'll put AlexNet dot classifier. That is the point, because we have changed our architecture here, right? And that we have assigned to AlexNet dot classifier. Anyhow, so this is the uh, you know we have to optimize the classifier parameter as the feature parameter are frozen. Right. Next is to train the model. And for training the model, it is the same step as before. That's a good news. Why? Because you can just do a copy paste here again and check this out. Copy and just paste, make one change because it is not CNN model, it is AlexNet. All right. So that is the new model here. And let me just check very quickly the other things as well. Okay. Yeah, by the way, previously when we did this, accuracy here, I did T by 80 and T by 30. This is because of the batch size that we are taking, right? So I'm just, taking a 1/10 of everything, right? In this training batch. Anyhow, that is gone. Now let me run this one more time. Again, it is going to take some time. And what I'll do, previously I saw that, over a period of time, I'm not actually gaining too much of the, improvement in the performance. So this time I'm not going to train for 20 epochs. I'll just train it for maybe 10 epochs. That would be enough. Okay. So let us train it for 10 epochs and then, come back and see what we have gotten, right? Let us run this. I hope it works perfectly fine. It's just a copy paste. All right, there we go. It is working fine. And it has started at 88% of accuracy compared to 86, not too far off. That's good news. But we'll let it run and then we'll come back and proceed from there.